Recording's rolling. It is Wednesday, April 16th. So I want to take a few days to do electricity and circuits with you guys. Even though this is not going to be on the AP exam, I've always taught this on my classes, and I really think it's worth your time to know. Uh, guys, quick show of hands. Is anybody considering maybe doing something with electrical engineering, possibly anything like that, or robotics or anything? Okay, so if you are, then what we're doing for the next few days is going to be vitally important for your career for the rest of your life anyway. So big good foundation. Uh, I mean, I'm really giving you guys kind of a truncated version of this. Like normally I would take at least 2 or 3 weeks to go over the stuff, but for you guys, I'm going to try to condense it down to a few days. So you don't pick up everything. At least the ideas will be out there. You'll have been exposed to these ideas. Right. Also, electricity going around in a circuit. There, you can apply this thought process to analogous systems. So if you're a pipe engineer, trying to figure out how to route water through a city, or if you're a traffic engineer, trying to figure out how to route traffic through a town, and say, okay, well, where do I want to put the stoplights? How's it going to change the traffic flow? There's an analogy to electricity going around a circuit. So it's a really similar type thought process. All right. So right, here's some of the topics we'll be covering. You guys, of course, have a page that looks like this in front of you. It has some circuits. Now, what these could represent is, right, you guys see this battery right here. You guys see some Christmas lights. If I hook this up, oh look, the Christmas lights turn on. You see that? Okay. Okay. Now, actually, what you guys are looking at right now, like this battery, these Christmas lights, is exactly the same as this one right here. Okay, so this one, right? This is a schematic diagram for exactly this scenario. Right? Well, I got Christmas lights open. Let me arrange them differently. Here's also 3 Christmas lights, but they're one after another. This is called in series. Right? Oh, look, they're not as bright as before. Same 3 Christmas lights, same battery, but they're just arranged differently. That is actually this one right here. So, like, why were these not so bright and these three are like super? Well, okay, I guess that one just burned out. Right. So, why are they different brightnesses depending on how I arrange them? Why could that be? Okay. And then on the opposite side are also circuits, but we're going to dig more into the circuits and figure out exactly what's going on in terms of voltage, current, power. Okay, these have units. Okay, so what's going on there? All right. So you guys can see all these concepts next few days, and I'll have you guys turn in this page and give you guys support on that. All right. So back to the AP exam, though. You guys know there are 30 days until the AP exam. Oh, by the way, all this electricity stuff used to be on the AP exam until I think if I remember right, I think it was the pandemic. I think when the pandemic, you guys remember? Did you guys get out of school? It was like in March, right? They just closed school for the rest of the year. I think that was the year that they just cut off all the electricity stuff and it just never came back. So you guys remember, of course, I pointed out to you guys, I posted a bunch of review links on Google Classroom, so you guys have access to those. There's AP Classroom, there's Flip in Physics, there's some other ones. And then you guys remember too, from your textbook, over the course of the year, I usually give you, like 30 or 40 different puzzles, but I only assign like 10 or 12 of them. So you have lots of spare puzzles that you guys can talk to each other. All right. So let's dive into this then. So first, what variables are we talking about? I got a whole list right here. So let's bring in electric charge. Now, this week when you see capital Q or sometimes lowercase q, anything to do with the Q, I'm talking about electric charge. Do I have a I do. Okay, let me blow up a balloon real fast. Got a balloon right here. It blows up. All right, that's right here. Guys, if I rub this against my hair, you guys ever done that? Rub a balloon against your hair? So this latex will steal electrons from my hair. All right, so now my hair is going to become positively charged and the balloon is going to be negatively charged. And see if I can get this to work. If I can stick this to the wall. About 50-50. Let's see if it works today. Today's a good day. Oh, look at that. Today's going to be an excellent day. All right. Today's going to be a Bill and Ted excellent type day. Look at that. So charge up the balloon, and you can quantify that in some number of coulombs. Okay. Now there's a positive charge and negative charge. Guys, what is positive and negative do? If it's positive and negative, attract or repel? Attract. Yeah. Right. So like charges will, if positive is going to repel, and then opposite, positive negative is going to attract. Okay. Right, now, if you can get that charge to flow, then you get what's called an electric current. You guys see this capital I right here? Right. So like C is used for so many different things. We're just gonna call capital I electric current, okay, the textbook standard. Okay. And how can you quantify how much electric current? It's gonna be in amperes. I'll usually just call it amps. And what is 1 amp? Okay, it's a rate flow of charge. So 1 amp per second. All right, so if you have a wire, so like I had these Christmas lights and hooked up to this battery, okay, there's some electric current flowing in the system. I have like this closed loop. As soon as I disconnect one side, the current doesn't flow anymore. Okay, so I need a closed circuit to get this current to flow. Okay. Now, why would current flow at all? Is because there's one of these going on, this potential difference. What's called voltage? I was usually just call it voltage. Now you'll see both these symbols used for it. Potential difference could be a difference of voltage, delta V, or some textbooks use epsilon, so you see that one too. And the variable is going to be volts. This is, I think, the only time in this entire class that I'll use the same character for sometimes for the variable in the unit, which is capital V, also measured in V. Right. So just careful about that. Okay. And but what is 1 volt? It's energy per charge, so joules per coulomb. Now I have some different batteries. Wait, do I? Where's my? Do I have a double A? Where's my double A? Well, you guys know what a double A looks like, right? Okay, I'll pull out a different day. I'll find one. But guys, how many? Wait, I do have a double A. I got a clock right here, guys. How many volts is this double A battery right here in this clock? Somewhere around here. It says 1.5. There it is. It's upside down and also probably fuzzy. But it says 1.5 volts. Can you guys take my word for that? 1.5 volts. Huh?
How many volts does a AAA battery have?
Guys, how many volts is a AAA? Little tiny battery. Still 1.5. Still 1.5 volts. Yeah, guys. Double A, AAA, those big old D cell batteries. Those are all 1.5 volts. Okay. Now the different sizes just means they contain different amounts of total energy. Like it probably last different amounts of time. Okay. But it's the same chemical composition. And that chemical composition, I have a poster for that later. I'll pull up. Provides a voltage difference. Right, it's the same voltage difference. It's always 1.5 volts. Okay. How about this boxy looking battery right here?
5 volts, 9.
9. Yeah. This is a 9 volt right here. Got 9 volt. 9 volt. Okay. And I'll pull out some Paul Hewitt demos later today. He's gonna have a car battery. How many volts do you think a car battery is?
Enough to stop your heart.
About 12. Yeah, maybe that too. Let's go with 12 volts. Okay. So I got 9 volts here. Double A is 1.5. Right. Now that potential difference. You see an analogy later. I'll use like an elevation analogy. Like why would a ball roll downhill? Well, if there's an elevation difference and a gravity field, so we that. Right. So you need a voltage difference to initiate some current to flow. Right. So is that. In fact, the relationship between these is called Ohm's law that we're about to get to. But you want some resistance also in your circuit. And now resistance, we're going to quantify this in ohms. So here's Greek letter omega for ohms, for resistance. Okay. In fact, yeah.
Where's the place that has less or more volts?
Yeah, so you look for a potential difference. So you go from like 9 volts to 0 volts, something like that. Yeah, something like that. Okay. Yeah, which way does current flow? Actually, that's kind of a tricky question too, because in a wire, what's actually physically moving in a wire?
The electrons.
Yeah, the electrons, right? Right. Which electrons have a negative charge. Now, back in Ben Franklin day, people didn't know that. They kind of knew there was positive and negative. They kind of figured that out, but they didn't. They hadn't verified the atomic theory of matter. They didn't even know what an atom would look like back then. So they just did a coin flip and they said, well, let's define electric flow as the flow of positive charge. And to this day, that convention is stuck around. So the motion of the electrons, which is from the anode to the cathode, so it's going from negative to positive, is defined opposite of the flow of current, which is, well, again, like defined as positive to negative, right? It doesn't really make any difference. So that's why the convention is just stuck around, but it's still interesting side note there. Okay. But guys, what if you did not have any resistance in your wire? Like, what if I take this paper clip and I just connect it to the 2 leads of battery? Now, I'm not going to do that because if I did, has anybody ever done that? What happens?
It gets really hot, real fast.
It sure does. That's exactly the phrase I was going to use too. Real hot, real fast. Yeah. And that has a name, because if you have a circuit that has no resistance, because this wire has pretty much no resistance, it's called a what circuit?
Fire starter.
Short circuit. Yeah. Yeah, fire starter. I like that one too. It's a little more descriptive. Yeah. If you were out camping and you had this right here, and you had a pile of leaves. Could you start a campfire with this? Yeah, sure could. Yeah, but it also drained the battery fairly quickly, so not gonna do that, right? That so some resistance you're looking for it and it's quantified in ohms. Okay. Now, how bright these lights light up? Remember, like here, okay, they light up, but they're kind of dim. Versus if I have them, what's called in parallel like this. Well, it's supposed to be a little brighter. Let's see, how about this one got disconnected. That's why I didn't turn on. Let me bring this guy back in here. Okay. Where I tie the leads together and then go across. Oh, that should have been really bright. These messed up.
Battery gone?
Yeah, that's a good question. I wonder if it's wrong guy. Let's bring back the Energizer. Oh, there we go.
wow.
Yeah, look at that Energizer. Those are real bright. Okay. So how bright the bulbs are is related to this concept of power in watts. Right? Actually, that's usually how light bulbs are rated, right? Like a 12-watt bulb or a 60-watt bulb, something like that. Okay. Oh, and you guys know what watts are, what power in watts is from this class anyway. Isn't that just a rate of energy transfer, like joules per second? Okay. Now, these concepts are all related to each other through Ohm's law and Joule's law, which I think I had on the title card here, right? Yeah, Ohm's law and Joule's law. So you guys can see those concepts later today. And then again, there's different ways to wire bulbs or resistors, you could say, right? So you can see all that. Okay? Now, these green lines down here is not going to be our main focus. This gets more into, like, if you bring in, yeah, okay. I'm mostly going to focus on these yellow lines right here, these gold lines. Okay, thanks. So, guys, good so far? Good so far? All right. Let's look at a few posters, and I want to get to Paul Hewitt here in a few minutes, but see what we got here. So electric field, here's what an electric field could look like. Now here, if I have opposite charges, then the field lines will connect. I did make a new poster, I haven't printed out yet, that if they have the same charge, then the field lines don't cross at all because they're trying to repel, right? But something like that. And here's the strength of the magnetic field. Q is charge in coulombs, D is distance, maybe in meters. And oh, look at that, got an inverse square relationship with distance. That looks kind of reminds me of a gravity field, sure, doesn't it? This K is the electrostatic constant. In fact, actually, next slide I got the value of electrostatic constant right here. This one version. Guys, does this look like universal gravitation? GMM over R squared? Yeah. Right? Just replace gravity with electric field and yeah, really similar looking concept here. Okay. How about this? Do you guys remember the gravitational constant was like 10 to the negative 11 in a bunch of units? This is 10 to the power of 9. So, whoa. No, just, no, kind of mix in apples and oranges because it's different units. Okay. But even aside from that, 10 to the negative 11 compared to 10 to the power of 9, which of those numbers is way, way bigger and therefore way stronger effect than the other? This one right here. It's not like 10 to the 20, right? 10 to the 9 compared to 10 to the negative 11. Right? 10 to the 20. Right? So, isn't this actually a much, much stronger force than gravity? Right? So, here, you can see that right here. Right? If this is dropping down, is it gravity pulling us down? But what's stopping it? Isn't it like a normal force stopping it? But really isn't it just like the electrons from the surface pushing against the electrons in this mass right here? Which is this right here, isn't it? Yeah, this is that's way, way stronger than gravity. Yeah. Oh, yeah, go ahead.
Electricity work the same like in all the universe?
Oh, yeah, that's a good question too. Does electricity work the same in a different universe? Now, we have no access to other universes if they exist, so there's no way to know scientifically. But that's a good question for speculation is like, why is this number what it is at all? Or why is the gravity field strength what it is? And we have no idea. They're just observed to be what they are. In fact, if you change these constants, these fundamental constants, you can show if you tweak it, in a computer model that very quickly you end up with usually just universes full of black holes and nothing really makes atoms or material or makes any sense. So like our world to have the materials they have, we kind of need these constants to be kind of what they are.
Properties of the universe are governed by about 30 numbers, and if
Yeah.
you tweak one of those numbers by a fraction of a percent,
Yeah.
everything goes to crap. So
Yeah.
the way it is now is really the only way it can be, I think.
Right.
Maybe
Yeah.
in other universes it's possible, but I think if you're going to have a multiverse theory, the numbers are going to stay the same, but the events are going to happen differently.
Yeah, exactly. Yeah. If there was, possibly like bajillions of other universes, right? Yeah, most of these universes just like full of black holes and like nothing is. Yeah. So yeah, just for us to be like aware and conscious, we're like kind of have to be in the universe that we're in for. Right? So, all right. Now there's lots of things you can put on a circuit. The main things that we're going to focus on for the next few days are just these two right here: battery voltage and resistor. Right now, you might see some of these other symbols too, but mostly you care about those. Right. So here's your battery voltage. Got positive, negative terminal. Right. Two parallel lines, one longer than the other. Right. Here's the my light bulbs are my resistors, so each of those could be a resistor right there. So yeah, it's a schematic diagram. Okay, here's my battery. Now there's different kinds of batteries. This battery might be this chemical composition here. So I mean, this is one conventional battery. You have manganese dioxide and zinc as your cathode anode, and you need some electrolyte in the middle. Maybe potassium hydroxide is a common choice. Right, and then if you can get some connection between this cathode and this anode, right, maybe some wire and throw some resistors in the middle, okay, then you have a complete circuit. Right, so you got that. Right. Here's a flashlight schematic. So here's your actual flashlight. Right? You pop in a battery and a bulb, and throw a little switch in there, right? On-off switch. Right. Now, guys, notice if you open your circuit, can there be any electricity flowing?
No.
No. Right. Again, you need a complete path between the cathode and the anode. Right. So you hit the on switch, bam, that's going to close your circuit. Right. That's represented by the switch. Right. The bulb is the resistor. The battery represents the voltage source. Right. You guys got that? Or basic schematic right there. Right. All right, let's do Ohm's law and Joule's law, then I'll switch over to Paul Hewitt. Yeah, over that. Okay. And so Ohm's law says how much current flows is voltage on resistance. Well, it's really potential difference. Most textbooks throw a delta V or epsilon. Something. Okay. So say I have a 9-volt battery and I got like 1 ohm of resistance. Yes, if I have 9 volts acting on 1 ohm, how much current flows? 9 amps. Yeah. Right. Of course, the metric system, the units all work out really nice. So volts over ohms would give you amps. So we got right. Okay. What if I have 9 volts on 3 ohms? 3 amps. Ooh, do you guys see by tripling the resistance, you get a third of the current? Guess that? More voltage, more current, more resistance, less current. Guess that too? Okay. All right, so Ohm's law right there. Okay. Now, when I was first learning this myself back in high school, I was sitting in class for like 2 weeks before any of this clicked. And this only clicked when I was told this analogy here. Actually, my mom told me this analogy. It's like, oh, okay, right now electricity finally makes sense. Right? So, because I don't know, electricity is invisible, but I can see like water going through a pipe myself. So if this helps you, this helped me. Right? So when I hear voltage, I think like pressure, like this battery sort of like a pump trying to push electricity through a circuit. Right? Resistance, think of it sort of being like a crimp in a pipe. So this resistor, think about just a crimp in the pipe. Okay? And the current that flows in amps, I think about being like a flow rate, like gallons per minute or cubic meters per second of water flow through, okay? Which actually works really nice as an analogy. I got a poster coming up, yeah, it's like a couple coming up, where if you just replace these values with their analogous values for water through pipe, it actually works like perfectly well. Okay, okay, so Joule's law, this has to do with power measured in watts, of course, power in watts. Right? How does that relate to the current and the voltage? Right? Now, there's 3 different takes on this. If you know any one of these and you substitute in Ohm's law, you can just very simply get the other 2. Right? Maybe we'll do that here. So current times voltage, like you know that one, power is current times voltage. Okay? How about this? What if you substitute in? Do you guys remember? Go back a couple slides here. Current could be voltage over resistance. Let's substitute that V over R, and for this I. So in place of this I, can I just do V over R? Is that okay? Okay. And that would be V times V over R. Is that true? Wouldn't that be exactly this one down here? V squared over R? Okay. Or you could rearrange this. Another common version of Ohm's law is V is equal to I times R. Is that okay? V is I times R. So I could substitute this V with I times R. And would that be exactly this? I times R, which is I squared R. Okay. So there you go. If you know any one of those, they're all a little bit different versions saying the same thing. Right. So here's a Joule's law analogy. Show you guys a Ohm's law analogy with water through a pipe. Here's Joule's law analogy. Okay. So let's go with P equals IV, power is current times voltage. Okay. So I got some voltage in this battery, 1.5 volts maybe. However much current ends up setting through depends on the resistance of this bulb. Okay. And if I multiply that together, I get how many watts end up flowing. Okay. Yeah, you can probably see when you buy a bulb from the store and it's rated like 60 watts or whatever. Okay. That's really only for a known voltage for, say, the American market. There's a particular voltage in the outlets. Actually, let's talk about that real fast, too. Does anybody know how many volts are in these outlets right here? Yeah, 120. Yeah, it's 120 volts. Also, it's alternating current rather than direct current. I'll show you guys an animation here in a minute. But this battery is direct current, and alternating current is a little bit different. Yeah, so this battery could be like 9 volts direct, and the outlets are 120 volts alternating. Anyway, that aside, and that'd be different in Europe. They have double the voltage in Europe, like 240s. Okay. So if you place the analogous parts, remember I said current is kind of like flow rate and voltage is kind of like pressure. interestingly enough, if you just pop in those analogous units, it actually also gives you watts. Right? So say if I'm out of power this paddle wheel or something like that. All right. Yeah, next one I got is how to wire resistors, but here, I gotta hit a pause point at some point to show you guys some video demos. So I definitely have a lot more posters to show you guys, but let's hit a pause point there and go over to some video demos. Let me find for you guys. Let's actually start with direct versus alternating current. Get this one on the board. Okay, so from a battery, it'd be direct current. Now, you guys see those red dots going from the positive to the negative terminal? Okay. But you guys just a few minutes ago, didn't you say it's actually electrons physically moved from the negative to the positive? Is actually what it would be. Let's start this right. But then, of course, this goes back to the probably about 18th century standard of, oops, they picked the wrong convention and it stuck to our textbooks this day. So it's actually shown the defined flow of current rather than the movement of electrons. Okay. Now, if you have alternating current, so it's not gonna. I should have looped this rather than sometimes it freezes. Well, okay. Let me reopen this, see if I can get that animation to start moving again. Right? Because the alternating current, if you watch real close, you open this file? No? The electrons have no net motion. You guys see it alternating, it just goes back and forth, back and forth, back and forth, but there's no net motion, right? And so it's a different kind of current that you actually want to use for the electric grid. And this goes back to 1890s. Do you guys know a history called the War of the Currents back in the 1890s? Yeah, okay, so some of you guys have heard this, right? So this is when people are realizing, okay, we can have a power plant, we can have some kind of distribution system, we can come up with an electric grid, we can power all these homes and businesses with electricity, which is really useful now, right? How do we want to do it, right? Which of these do I pick? So anything is battery operated, which could be like this clock right here, or your cell phones, or your laptops, or if you're wearing a watch, anything is battery operated is going to be just a direct current. Okay, but anything in that power grid, it's more useful to have alternating current. And the reason is for alternating current is it's easier to step up and step down voltages. And really, what you want to do with a whole electric grid is, okay, I don't know if this is too much information at this point, but here I'll just go show you this the way. Right. So you get this analogy with like water movement. I'll give you guys a water analogy here. Okay. Let's say you have some water treatment plant. This would be a water treatment. Okay. You got a bunch of houses you got to route the water to. Okay. Now, say what would make more sense? Should I route pipes to each individual house, and then these people are turning on and off their faucets and the showers and the dishwashers, and the current in this pipe's going like start stop start stop start stop. This poor water treatment plant is having trouble pumping. Or should you do this? Should you instead route all the water to a giant water tower up here, water tower, and then that water tower can go to each individual house. And now as people are turning on and off their faucets and their showers, right, all the water levels doing in the water tower is just going, kind of fluctuating up and down a little bit. And this water treatment plant can very simply pump water in and replenish it at a constant rate. Does that make more sense? Okay. So if replace the water tank and the water and pipes with electricity, and what this represents then is a high voltage and a low current, rather than a low voltage but constantly changing current. Okay, so now you have a power grid that makes a lot more sense. Okay, so those power lines that you see outside, those might be like tens of thousands or 100,000 volts. Right? Let's call it 100,000 volts. Okay, so high voltage, but the current moves extremely slowly through. Right? And then because of Joule's law, remember Joule's law is power is current times voltage. That's Joule's law. Okay? So if you have a high voltage, you can have a low current and still transmit all the energy, because that's what power is a rate transfer of energy. Okay? Right. And it's easier to use a transformer to step down the voltage going to each individual house. So you have some transformer here. You can step down the voltage and increase the current and then route it into all these individual homes. Okay? You see that? Right, so that's why alternating current rather than direct current. All right, let's flip some Paul Hewitts here. See how far we get here. Paul Hewitt.
This is called the Van de Graaff generator. It's named after a person by the name of Robert J. All right, we be learning this stuff. All right. Now, what we're going to do here, it's talked about in the textbook. It turns out this belt is going to carry charges from little lightning points here, deposit them up in here, and we're going to build up an enormous charge on the top. Let me show you what I mean. Notice I am, notice that I am keeping, I am keeping this closer to the dome than my head. Guess why? I don't want to put my head closer than this, all right? Let me show you that that does charge. Let's try this game.
All right, here's actually why I wanted to roll this video, because you guys saw the Van de Graaff a few weeks ago anyway, right? He has a stack of pie plates there. They're all metal, right? And, what do you think is going to happen?
Resistance.
Ooh, right. Now you guys know it's a giant charge right there, right? Guys, are all the pie plates about to get the same charge? Like they'll all be charged, maybe positive, maybe? Hey guys, if they all have the same charge, what do? Aha! Aha!
And so the flow of current is proportional to voltage difference. Not how much voltage, but how much voltage in one place compared to the other. Think of voltage as a pressure, huh? So it's proportional to voltage difference. Proportional to. So the more voltage difference, the more. Hey, imagine I have a pipe right here filled with water. Okay, see that water filled pipe? I have a piston over here and I have a piston here. And I push with a certain pressure, maybe 5 units. I push with the same pressure here, 5 units. Which way does the water flow? Instead of water, ain't gonna flow at all. I say, yeah, I got under pressure. And you say, yeah, but there's no pressure difference. How about I push here with 5? And I push over here with 3. What does the water do, gang? What does the water do? The water flows, okay? And similarly, if you take a piece of wire and you put a pressure difference across the wire, and I can do that here. Here's a lamp, okay? This is a 12-volt battery. One end is 12 volts higher than the other. If I touch here and touch here, no light. If I touch here and touch here, no light. There's 12 volts, 12 volts. Why no light? Check your neighbor, why no light? Let's try the other side. No light, there's still no light. Why, how come? But I got 0 volts over here. Oh, I got 12 volts. There's no difference. You gotta have a difference. Look at him, I go like this. Ought to be, huh? What's the voltage difference across the lamp now? 12. So if you got a voltage difference, you get a current. It kind of makes sense. This is not counterintuitive. The more voltage difference you have, the more current you're going to have through a conductor. And this is a conductor. It's a piece of wire made out of copper where electrons can flow all through there, gang. So I have a conducting path with a voltage difference. No voltage difference, no current at all. Voltage difference for a current. Make sense? When you touch a wire, a lot of times people touch a wire and they can't let go. You know why they can't let go? People, oh, they attracted to the electric. No, he ain't attracted. Contraction. Remember the biology experiment you used to do, the frog's legs, the frog leg like that, and you come over and you touch it. Frog is dead, honey, and it's still going like that. It turns out it's an electrical. Can you guys do that? Try it. I hope you can. Do you know what you guys are doing? You are sending electrical impulses down your hand. It's electrical impulses that do that, and it contracts. So what happened when you touch the wire? It's not that you attract, it's that your fingers contract. So he told us that electrician types, always if they're fooling around, they touch like this. If you touch like contract, you pull away, see? You're okay. But you don't want to go like that. You know what I'm saying? Practical stuff. Hey, why is it that you see birds on high tension wires, bare wires, and you see the bird come down and he grab on the foot and stand on one foot and he's on the wire? And the bird doesn't get fried. The bird's okay. Now what happened? The bird reached down and put the other foot on the same wire. What happened to the bird then? Begin with N and with nothing. Try it. Nothing. He said, bird's okay. Look, hey man, the bird's 100,000 volts. Is the bird all right? The bird is all right. Because you get 100. What's the voltage difference across the bird? Zilch. This relationship, current proportional to voltage difference, becomes an exact equation when I include the idea of resistance. If you have a humongous resistance, even for a big voltage difference, the current will be very small. So how much current flows through things has to do with two ideas again. What's the voltage difference across the ends of the conductor? And what's the resistance that that conductor offers to a current flow to begin with? And that usually has to do with the geometry and the material of the conductor. Like a great big fat piece of copper has less resistance than a little skinny piece of copper. Just like a great big humongous pipe will have less resistance to the flow of water than a little skinny pipe, yeah? And how about a lamp like this? This copper right here, it's relatively thick, but it's very, very thin in there where the filament is. Guess where most of the resistance is across these two leads? Begins with FIL. Filament. In that filament is most of the resistance. And guess where most of the energy is dissipated going from here to here when I touch it across the battery? Right in the filament. In fact, the filament reacts so bad, it turns white hot with heat. Look at that. It's glowing. And there's your lamp. Isn't that nice? So we measure current in amperes, amps, okay? And we measure voltage in volts. And we measure resistance in all together now. Ohm. Okay, there's an ohm, yeah, that's ohms. In fact, ohms are written like this. Greek letter omega, ohm. Voltage is written like this, V, and current is N. Amps, the unit is amps, and oftentimes we call current I. So we could say I equals V over R. And it's the old song and dance gang that if you know two of these things, you know the other. Like, for example, let's suppose I tell you the resistance of this little lamp is 1 ohm. And I put it across this 12-volt battery. There are people in this room besides Lee who can tell me how much current is flowing through the battery. And then there are people that can't. Check to see if you're sitting next to someone who can. 1 ohm resistance, 12 volts across the battery. What's the answer again? 12. And that's 12 amps. That's Ohm's law. And here's, I'm
All right.
gonna hook this up.
All right, guys, but before I roll this one, let you know a couple things. This is the last Paul here you guys see today. This one's pretty long. It's like 5 or 6 minutes long. And there's a ton of information packed into this. I haven't shown you guys how to, actually, you know what? Here, I'm gonna switch over. I'm gonna switch back to this one just so we can break this up a little bit. Okay, because right at this pause point, I was about to go into how to think about resistors. Okay, so if you see resistors one after another, that's like this right here, resistors one after another. The term for that is called in series, just like that title shows, in series. Okay, and the total resistance, you just very simply add them up. That's all. Okay. Now I've been using a water and like a water pump analogy. Like this could be your pump right here, your battery. Okay. There's another analogy Paul Houston uses too, particularly for current and amps. You think like traffic flow, and these resistors are kind of like stoplights. In fact, if you're a traffic engineer, this might be really helpful to your job one day. Okay, because every time you add another traffic light in series like this one after another, doesn't it just like increase the total stopping time for the cars? Right. So you just very simply add them up. So that's fine, right? Okay. Now that's different than wiring resistors like this, which is called in parallel. Let's see. You guys see where I have like these leads tied together for these Christmas lights? I'll get some of these in your hands in the coming days too. Okay. And look there. Oh, well, whoops, that's my. Let's get the better. Right. That's where they turn like super bright, right? Okay. Now, every one of these individual bulbs has the full 9 volts going across it, right? Versus, well, when they were serious, here, nobody say this, but yeah, so it's still a 9-volt battery, but the voltage drops a little bit at a time, so it drops 3 volts, 3 volts, and 3 volts. Okay, so different way to do it, right? But what about the total resistance for the entire circuit? Like if each of these bulbs was 1 ohm, then the total resistance here is 1, 2, 3 ohms. Okay? But in this case, the resistance is actually, from the point of view of the battery, there's actually less resistance. And it makes a lot of sense from the point of view of the traffic analogy. Okay? So you guys see this battery down here? Battery right here? Bam. Suppose this was like a parking garage. And I got a bunch of cars, and the cars leave the parking garage. And they got to drive around town to get back to the parking garage. Okay? Well, if all you had was that, then wouldn't all the cars have to go through those stoplights? Okay. But what if you're a town planner saying, hey, let's open up a new street and let's have another stoplight? And then let's open up another street. Let's have another stoplight. Well, because every time you add more and more stoplights in parallel, does that actually make it easier or more difficult to drive around town? Easier, because now you have more options about how to get around. Like if there's 100 cars driving around, right now they're going to kind of split up, right? And they're kind of divvy. Right? It's going to get easier to get the traffic to flow through. Isn't that true? And the total resistance actually decreases. Now the math behind this, there's a proof that leads up to this, but I'll just cut straight to this. Right? Is there's two ways you can solve it. Right? One way is you can add the reciprocals and then take the reciprocal of those. Right? So here, for example, let's do what if this was about 30 ohms, 30 ohms, and 30 ohms? Here, I'll write this down. But what if it's 30, 30, and 30? What would the total resistance be? Well, I could do 1 over the total resistance is 1 over 30 ohms plus 1 over 30 ohms plus 1 over 30 ohms. Okay. Now 1 over 30 plus 1 over 30 plus 1 over 30 is not like 3 over 30. 1 over resistance, and this is resistance total. Let's say I'm solving for that. Is like 3 over 30. Oh, wouldn't that be true? Okay. Is that like 1 over 10? Okay. And then if you're solving for the total resistance, can I just very simply take the reciprocal? Okay. And that would be how many? 10 ohms. So even though each individual resistor is 30 ohms, you guys see the collective resistance would only be 10? That'd be a third as much. Okay. You have 3 resistors in parallel, you get a third of the resistance. You guys see that? That makes sense? Okay. Right. Now there's another way. If you go through the math, you can do product over sum, but the catch is you can only do 2 at a time. Right? Like if you bring in a third one, well, you have to break this part process. Right? Like here, guys, what if I just do 2 in parallel? Okay. So let's do that. What if I do? Let's stick to 30 ohms. So if I do 1 over R equals 1 over 30 plus 1 over 30. It's gonna be ohms. All right. Do you guys think it's going to come out to 15 ohms altogether? Probably half, right? Okay. Now you could do that. Okay, so I do 1 over 30, 1 over 30, that's 2 over 30, and then take the reciprocal of that. Yeah, it's definitely 15 ohms. Definitely 15 ohms. Okay. Now, if you went through a math process, could you get a? Well, if they were different, you get a common denominator. Right? But 1 over R equals. You guys know it's going to be 2 over 30. Okay. So R is going to be 30 over 2. Okay. And what you can show in general, like if this, yeah, I should have picked a different example where they have different denominators, but if you need a common denominator, what this always works out to is product over sum. Let me show you guys it's the same thing. So this is definitely 15 ohms, right? Definitely 15 ohms. Okay. What if I did product over sum? What if I do 30 times 30? Whoops, sorry, ohms. 30 times 30 over 30 plus 30. This is also ohms. Okay. Would that be 900 divided by 60? Is that what it would be? 900 divided by 60? Okay. See if you guys are following. Guys, when I hit enter on this calculator, what number has to pop up on my screen? 15. Yeah, there it is. It's 15. 15 ohms. Right. Guess that? So it's the same thing. Product over sum. Now the catch is that only works for 2 at a time. Now you can do all 3, but you just have to break it into smaller steps. So what I would do is I would start with resistors A and B, do product over some of those, write that number down. And then I can draw an equivalent circuit and treat this as if it's a single resistor, right? Like a single 15 ohm resistor. Let me show you that works too, because actually I'm really close to showing that. So suppose I did that just for these 2 resistors. Can I draw an equivalent circuit like this? Right. So I still got this 30 ohm guy here. But now these 2 collectively, it's as if it's a single 15 ohm resistor. That's what we just did, right? Right. And if I do product over sum between those 2, what answer do I have to get again? Did we just do that a minute ago? Remember, all 3 of them comes out to 10. You guys remember that? Right. So let's see if I do product over sum, I have to get 10. So let's do resistance total is I can do product over sum. This is going to be some number of ohms at the end of the process. Right. It has to be 10. Let's see if it is. What's 15 times 30 over 15 plus 30? Yep, it's definitely 10. Of course, it's going to be, right? Okay. Now it would be a multi-step process using product over sum, but you can only do 2 at a time. Okay, guess that. Okay. All right. Right. And then, in time, we'll break out the multimeter. Okay, but I got to play this Paul Hewitt for you guys. Right. So there's a little bit of groundwork. Let's go back to Paul Hewitt. Right, and here's like the full story of really everything. Well, pretty much everything I want you to know here.
I'm going to hook this up like that. And lo and behold, it lights. What's the voltage across the lamp, gang? 12. What's the voltage across the lamp now? 12. What's the voltage across the lamp now? 12. In fact, you know what I could do? I could keep this battery in this room. And I could take these two leads and I could bring them to the other side of campus. And over on the other side of campus, I could go like this. And I'd say, what's the voltage across the leads, gang? And what would you guys say? 12. And it would light up over there. In fact, what do you think a wire is? A wire is just two leads that come from some power source somewhere else. But you got one of these things cut off. You hit a switch, boom, you connect it and you're on. See, it's like this. Turn the switch off, boom. Turn the switch on, boom. There's little clever ways to do that. But I've got 12 volts across that lamp no matter where I put it. Okay? Let's suppose I go like this, gang. Let's suppose I put another lamp in here. I'll put another lamp in series. Series, I'm using a word, gang, series. Huh? There's one right after the other. I should have asked you before I did it. Will a lamp glow brighter or less bright? And you guys would have said anyway, it's less bright. And I say, what's the voltage across the two lamps? And you guys would have said, what's the voltage across one lamp? And you guys would say, yeah, feels good, feels good. 6. 6 and 6 is what? 12, that's right too. If you take the 6 volts across this 1 ohm, what's the current in there? But we gotta go through that again. If I get 6 volts across there and the resistance of 1 ohm, 6 amps. 6 amps here. How many amperes over here? 6. In fact, in this series, how many amps right through this little point right here? How many amperes through a point right here? 6. And how many amperes through the battery? 6. 6, 6, 6, 6, 6, all the way along. How many amperes up here? None. This is not part of the circuit.
Okay, now how he goes through this, he tends to do it from a micro point of view. He's saying like, if I follow what's the current and voltage drop doing at every individual part, which is one way to think of it. How I usually approach it is more from a macro point of view. It should be more like this. I know it's a 12-volt battery. Guys, look at Ohm's law on the back of the board. I equals V over R. It's a 12-volt battery. He has 2 resistors in series. So isn't that 1 plus 1 is 2 ohms down here? So you can do 12 over 2. That's a different way to also get 6 amps. Okay. Remember, current in amps is kind of like traffic flow. So it's like 6 cars have to go through all the stoplights in the series. Okay.
The circuit's right through there. See what I'm saying? The current flowing through the circuit. And the circuit now has twice as much resistance as before. If it get twice as much resistance, what's the current? Half as much. Do you see? Ohm's law kind of says it all. Ain't that neat? All right, now here's what I'm going to do. And everyone's going to get this right. I'm going to hook another lamp in series, and I'm going to connect it up, and you're going to tell me brighter or dimmer. Is there anyone says brighter? No, nobody say brighter. And what do we got? It sure is dimmer. Let me ask you guys a question. What's the voltage across the whole system? 12. Okay. How much resistance we got now compared to before? 3. 3 times the resistance. How much is the current now compared to with a 1? 1/3. Ain't that neat? So now you got 1/3 of an amp. Huh? What's the voltage across?
He meant to say 1/3 as much, which would be down to 4 amps. That's what he meant to say.
It's one of these things. 1/3 of 12. 4. Okay. And 4. 1 ohm. Oh, do I have it right? Did I make a mistake? Did I make a mistake, gang? I never make mistakes. But we have 4 volts across here. Okay, yes. 1 ohm, so we have 4 amps. What's going through here? 4. 4. Before it was 6, and first of all, it was 12. So the current's getting less and less because the resistance getting more and more. This is a series circuit. I'm going to make a little change, gang. Look how come it's bright. How about I take a lamp now and I put it not in series, but in parallel, like the rungs of a ladder, parallel. I'm going to hook this. What's going to happen to the brightness of that lamp when I connect this? How many say nothing? My people, that's right. Because let me ask you a question. What's the voltage across this lamp? What's the voltage across this lamp? What's the resistance of this? So what's the current through this? 12. 12. What's the voltage across this lamp? 12. What's the current through there? 12. 12 divided by 1, get it? 12. 12 amps, 12 amps, 12 amps. To be amps, volts, I get mixed up again. Voltage is the pressure supplied by the battery, 12. There's 12 right through across these, from these 2 prongs, yeah? and I pick up the 12, 12, 12. The battery gonna wear down fast now, gang, because I got a lot of amps flowing. If there's 12 amps flowing through here, how many are flowing right through here? 12. It's like automobiles driving from a garage down here. And some of those automobiles go through here and come back. Some go through here and back. Some go through here and back. If 12 go through there and you put a little checkpoint right here, how many are going through here? 12. Okay? How many through here? 12. How many through here? How many through here? Ah, what is it? It's 24. Because you get the 12 from here and you get the 12 coming down this street. How many through here? 24. How many through here? You guys are on 12. How many through here? 36. How many through the battery? Who's getting tired? The battery, the battery. More energy going out, no, more power going out. You get it? Okay? Think about these ideas.
All right, last thing. I know some of you guys have been out this week for different reasons. I know there's still a lot of testing going on. If you miss any days, just watch the videos. You'll be fine. But here's a new review page I gave most of you guys a couple days ago. Guys, who does not have this review page yet? Who does not have this? Yeah? Oh, everybody's got this? Oh, awesome. Okay. You might notice too, on the back side, the bottom 2 rows are electricity. All right, so that'll have to be a wrap on today.
I have a question.
Oh, yeah.